All right. So as I said, I would go over and double check everything, especially because, whenever, as with most people, whenever we realize we're running out of time, I definitely can make a mistake. So I wanted to go through and double check everything. And I also wanted to do an example. This example 5 had no solutions, and that happens. There's an example of that in your book, so that's not, a totally out of character thing. However, I had originally just wanted to use an example that did in fact have solutions. So I have a different example that does have solutions, so we can show how that works. But I also looked back at this problem right here, this number 4. I don't know why it's number 1. It should be number 4 right here. Yeah, it originally said 0 less than or equal to theta less than or equal to 2 pi, but I skipped over that. I did this all and then was like, oh, all solutions were done because this box is done for all solutions. That's totally correct. But I want to make sure that we know how to do it for taking into account these boundaries. Now, 0 to 2 pi, there's actually going to be many solutions, like 7 or 8. So I'm just going to, I change it to just 0 to pi, just so there's, less to worry about. So I just want to make sure we see how that works. So everything we've done up to this point is totally correct. We've landed at theta equals pi over 24 plus k pi over 4. But we want to make sure we get all solutions, right? This is why it's good to go through and highlight and make sure so we don't skip it. All solutions in this range, or in this interval of theta, we'll call it that. So let's just start plugging in k's. So when k is equal to -1, that is theta over 24 plus k pi over 4. Now I went ahead and rewrote this theta as pi over 24 plus k, plus 6 pi over 24. And the reason why 6k pi plus over 24. Now the reason is just to make our lives easier, right? Now that we have 24 on bottom, we can add and stuff like that. So we'll say if k is equal to 1, then theta equal to -1 equal to pi over 24 plus 6k pi over 24 is actually equal to, this would be -6 pi over 24. You get -5 pi over 24. That's out, right? That's out of bounds. So that's not going to work. How about k equals 1? So if you do this, you get theta equals pi over 24 plus 7 pi over 24 is 7 pi over 24. That's good. K equals 2, theta equals, you get pi over 24 plus 12 pi over 24 is 13 pi over 24. That's good. K equals 3, you get pi over 24 plus 18 pi over 24 is 19 pi over 24. That's good. However, if you did k equals 4, you would end up with, well, 24 pi over 24 plus pi over 24 is 25 pi over 24. That is not good. So k can only equal 1, 2, or 3, which means that our solutions are theta equals, when k is 0, right, that's just the baseline, and that is just pi over 24, or when k is 1, so 7 pi over 24, or 13 pi over 24, or 19 pi over 24. And if we were to keep going, then you would have, like, if it were 0 to 2 pi, then you would end up with, 25 pi over 4 plus 24 plus 31 pi over 24 plus 37 pi over 24, and so on and so forth, and until you ended up with, something greater than 48 pi over 24, and then you'd be out of bounds. So yeah, 25, 31, 37, 43, you're good there. And then 43 plus 6, you'd end up at 49. You're in trouble. Yeah, you've gone too far. So this is the set of solutions if we want all possible solutions. So this would be all possible solutions if this weren't here. But because this is here, we have to say, okay, what values of k are going to work? And k equals 0 is the first one. So that's just pi over 24. And then we tried k equals -1. That was out of bounds. But k equals 1, 2, and 3 did work. And so we end up with these solutions. All right. So let's do another example. With this piece, this totally worked out, and I went ahead and did this an alternate way, and this is totally correct. There are just no solutions. In the real numbers, in the in the complex numbers there are, but there are no solutions. We're done. So this is a possibility, but I want to make sure that we see how to do this if if we do actually end up with solutions. So I see this cosine squared. I'm thinking Pythagoras. So I am going to write this as 2 minus 2 sine theta equals 4 times 1 minus sine squared theta. I'm going to distribute the 2 across. This is 2 minus 2 sine theta equals 4 minus 4 sine squared theta. I'm going to bring everything to the same side. 2 minus 2 sine theta minus 4 plus 4 sine squared theta equals 0. I'm going to combine like terms. So I should end up with -2 sine theta minus 2 plus 4 sine squared theta equals 0. I am going to rearrange to make life a little bit easier. So I'm going to have 4 sine squared theta minus 2 sine theta minus 2 equals 0. Well, I see that they all have 2, so I'm going to pull a 2 out. So I get 2 times 2 sine squared theta minus sine theta minus 1 equals 0. And I can divide the 2 out, so we're good. Now, I'm going to say, look, I'm just going to say x is sine theta. So this becomes 2x squared minus x minus 1 equals 0. Now I want to factor this. This factors by 2x and x. Now, this piece and this piece have to multiply to be -1, but add to be -1. So one has to be negative, one has to be positive. So if I do this, then let's see what happens. I get 2x squared minus 2x plus x minus 1 equals 2x squared minus x minus 1, which is exactly what we had originally, right? So we're good. We factored it correctly. So I have 2x plus 1 equals 0, or I guess I should say and, x minus 1 equals 0. But remember, x is just sine, so now we're going to plug in our sine. 2 sine theta plus 1 equals 0, and sine theta equals 0, minus 1 equals 0. This gives us sine theta equals -1/2, and sine theta equals 1. All right, let's double check our handy dandy unit circle to see where this happens. So sine of theta is equal to -1/2 at 11 pi over 6, and should also be at 5 pi over 6, 7 pi over 6. And sine of theta is equal to 1 when theta is equal to pi over 2. So remember, we have to be super careful. I have underlined the solutions between 0 and 2 pi. So technically, I could go down here and say theta is equal to 11 pi over 6 plus 2k pi, or 7 pi over 6 plus 2k pi, or pi over 2 plus 2k pi. But here's the thing, if I'm only looking for the intervals 0 to 2 pi, if I add or subtract 2 pi to any of these, I end up outside of my bounds. So in fact, k has to be 0 for all. This means that my solutions are just theta equals 7 pi over 6, 11 pi over 6, and pi over 2. So I wanted to go back to this problem because I realized that part of my reasoning was incorrect, and I want to go through and really show what that looks like. So I said that you find the period like normal, right? So we did 2 pi divided by omega. Omega is 4, so 2 pi over 4 is pi over 2. And then we found phi over omega is pi over 4, and that is half of the period. All of that up to that point is correct. The issue was I then said, all right, so because you've shifted it half a period, then that means that on the end, you're going to only have space for a half a period. But the more I thought about that, the less sense that made, because this original problem was supposed to be easier than that. So, and it turns out that it is easier than that, right? When I came up with this over the weekend, this was a much easier problem than it was when I was going with y'all, and that's the mistake. But that's also the crux of the problem, is that you do, in fact, when you shift it, you end up cutting off part of the period. But you actually do end up getting that part of the period at the end. So let's see what that means. Let's go over here to our Desmos function. So here we have just sine of 4x plus pi, because remember the -3 and the -1 don't change the period or the phase shift. So I just started with sine of 4 theta plus pi. So we can see that it has definitely been shifted by pi over 4, right? Our phi over omega. If we put our cursor right here, we see pi over 4, 0. That is normally sitting at 0, but it's been shifted. So what that means is that we start here at pi over 4, 0, and we are going to do one full period, which is pi over 2. So pi over 4 plus pi over 2 is 3 pi over 4. And then we're going to do another period, which brings us to 5 pi over 4, and then another period, which brings us to 7 pi over 4. And then we just have a half of a period right here. So that point is correct. The trick, however, is that we see that we have a half a period here. So this turns out to be a half a period here, 3 full periods here in the middle, and then another half a period at the end to give you a full 4 periods. So the idea is that the phase shift doesn't actually change the number of periods, it changes what they look like, right? Instead of having a nice starting at 0 going up, down, up, down, up, down ending, we end up shifted. So we have this half a period from 0 to pi over 2, or excuse me, pi over 4, and then every pi over 2 we have a full period, right? But this means that we have this extra pi over 4 here at the end and this pi over 4 here at the beginning, which adds to pi over 2. We get a full 4 periods. So if I turn this one off and turn this one on, this is what it looks like fully transformed, but it's the same thing. It's flipped and shifted, but the period or shifted up and or down, right? In this case, it's been shifted down, but the period hasn't changed and the phase shift hasn't changed. Similarly, with the second piece, tangent, we end up with the same situation where you have, excuse me, this should have 2x plus pi. Right, so you end up with the same situation where you have 3 full periods here, but then you have a half a period here, which is the phase shift, and then a half a period here at the end. So you end up with a full 4 periods. Now remember, it's 4 periods for this tangent because the period of tangent is normally just pi. So for example, if I were to just come over here and change this to pi, I get a full period here in the middle and then a half a period on each side for a full 2 periods in the interval 0 to pi, which makes sense because our normal period is pi, we divided by omega is 2. But I asked you to do it from 0 to 2 pi, so we just double it and we get 4. So that was the mistake. You do end up losing, right? I want to reinforce this. You do end up, when you shift, cutting your period a little wonky. But what doesn't happen is you don't lose that extra piece. That extra piece is tacked on either at the beginning and the end, right? So the beginning and the end have those pieces that you would have cut off. So you end up getting the full period. So what that means is that the phase shift doesn't change the number of periods in an interval. It changes what they look like. And that was the original point of the problem when I created this over the weekend, but I did not quite remember that that is what I was trying to show. So I apologize for that. I hope that this Desmos has made sense of why that's the case. The shifting does matter. It does change the way the periods look, but it does not change the number of periods that are going to be in an interval. So if anybody has any questions about that, please let me know. And as a final note, I had down here, I didn't put a -2, right? So this is shifted down 1, so this 1 got shifted down to 0, and then this -1 got shifted down to 2. I'm pretty sure I said that, but didn't actually write that, so I just wanted to make sure that we had that down here. All right, on that note, we should be good. If there are any questions, please don't hesitate to reach out.